Do you need any water? Do you want a cup of water or anything?
Yeah, I'm okay.
Okay.
Yeah. Okay, let's get started. So it's my distinct pleasure to introduce two speakers today. One of them, Ray Simmonds, comes from NIST in Colorado, and the other, Sam Mitchell, is actually local here, but not in the physics department, in the dance department. He's an MFA student in the dance department. And I'm very excited to introduce this very interesting collaboration that they've started to explore internet connection between physics and dance. Ray got his PhD from sort of state school, Berkeley. Not only did he pursue mechanical engineering and physics, but he also pursued dramatic arts and dance. Following his graduate studies, where he has a PhD in 2002, he did his research, his thesis research on superfluid helium-3 Josephson weak links, and led to the development of the first superfluid helium-3 DC squid. And I don't have to spell that out in this class. Following that, he briefly studied quasi-particle states and high-temperature superconductors as a postdoc at UCB. And then since 2002, he also received the National Research Council postdoctoral fellowship for NIST, and he joined the NIST faculty as a staff physicist in 2004. Among the many things he's accomplished, he's identified two-level system defects in Josephson tunnel barriers with superconducting qubits, demonstrated coupled phase qubits via simultaneous state measurement, and that's going to come up. Demonstrated the first quantum bus memory with superconducting circuits, developed vacuum gap capacitor, blah, 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 2010, and achieved strong coupling in a new circuit cavity electromechanic system. So I think we can say you're working in the field of quantum computing, but actually working with the hardware in many degrees. He has, throughout this, has remained in some interest in his artistic endeavors, and so this has been an opportunity to sort of express that. Now, Sam has been training in dance for over 20 years. He was also at the University of California, Santa Barbara, and I think they're going to talk about the connection there. He's explored improvisation, performance art, theater, formal dance training in ballet and modern technique. He's continued his training in the Bay Area with Joe Good, Kim Espino, Kathleen Hermersdorf, and Augusta Moore. He also performed with Summer Ulrichsen and her company Torque, which is a good physics company name. From 2000 to 2006, he was a core member of the Santa Barbara Dance Theater, and he worked under the direction of Jerry Pearson. He toured nationally and internationally with this company. From 2007 to 2009, he studied with the City Company, directed his own dance studio in North Park, studied the Meisner acting training with Lisa Berger, and choreographed Chuck Mee's Big Love in collaboration with the Cal State San Marcos Theater Program. He's also collaborated with director, artist, and Fulbright scholar Andrea Pulley in her film The Wave, Physics. In 2010, he joined the Patricia Rincon Collective. Patricia Rincon is actually the head of the undergraduate and graduate dance group at here at Ucsd. But she has her own private collective, and he joined that in 2010. He has toured internationally with that as well, in Switzerland, Buenos Aires, Argentina. He performed at the Tanz and Lowton International Dance Festival, and additional performances in Zurich. So he is in his last quarter at UCSD in the MFA program. He has created several works here, particularly site-specific dance works, including Erhaben for Arts in Action, Ex Machina with David Jacoby at the Wagner Play Festival in 2013, Huerta 13 for New Directions concert in 2013, Hedin in collaboration with the Oslo, Norway choreographer dancer Siri Jontvedt, and Snell Hall for the Without Walls Festival. Deer Spine for Bradford 2014, and Duanas Novum, which will be performed in this January. So there's two performances in January.
There's actually three.
There's
so
three,
it'll
yeah.
be
Okay.
and we can give more information about that, but it's going to be at La Jolla Playhouse, January 23rd through the 25th. January 23rd and 24th at 7:30, and the Sunday, which is the 25th, it'll be 7.
So this is the performance that this talk is based on.
Yes.
Yes. Okay. So without further ado, please
Thank
take it
you.
away.
So yeah, it's a pleasure to be here, especially in the warmth, the nice sun.
because it's freezing in Colorado right now. And I want to thank Adam and Dana for helping out with logistics, and Doosan also. I don't think I met it. Am I saying his name right? Okay, thank you. So yeah, it's a pleasure to be here, and we're going to talk today about quantum statistics, effects on human dancers and the observer. So I'm going to start off with a rough outline to give you an idea of what we're going to talk about and where we're going with this. So we're going to first introduce some connections between art and science, then talk about some examples of people out there in the world that have been trying to integrate art and science. Then we'll talk about our collaboration with trying to merge dance theater and quantum physics. I'll do a brief review of some of the physics concepts involved. Sam will talk about some of the dance concepts involved. And then we're going to talk about how did we actually generate this performance. And at the end, what did we gain by doing this? And we're still going since we haven't had the performance, so there's more to gain. So I wanted to start off with talking a little bit about Leonardo da Vinci and the time, in the time that he worked in the Renaissance. Even though he was a remarkable character and had interests in both art and scientific concepts, engineering, all these things, he was a remarkable figure. But at that time, it wasn't so strange to be working on all these different things. That was something that people did. They were interested in different things. It wasn't so broken up. And one thing we just wanted to touch on, if you look at sort of a history of an art timeline, and I'm going to flash a history of mathematics, and this is ancient philosophers. It's interesting to sort of look at in the modern era, which is really this last right portion, we really see diversification in terms of art and sciences, and even within fields, they start to diversify more and more and more. And we just have this kind of rough idea that when things start to diversify and split up, you sort of lose connections. And part of what we're trying to say is we all came from the same source. We need to reconnect and not get stagnant. But one thing that I noticed, which is really interesting, is in this time from 250 BC to about 250 AD, there's this sort of gap of not much happening. Even with philosophy here, there's a gap where there's just not much happening. And if you go back to the artistic timeline, you notice that's really when the ancient Roman Empire was doing their thing. I don't know what that means, but I just think it's kind of interesting that something got killed during that time. So really, the arts and sciences got more specialized. They separated even within fields. Different ways of thinking have emerged from this isolation. And then fundamental differences in the motivation and purpose for both sort of art and sciences. In science, we're somewhat motivated by, practically by what funders want, who's going to pay for it, what do they want? They want results. In science, we want to create new technology. We want to make practical things that do things for you, that make life easier. And so that there's a motivation there that kind of drives it. In arts, it's a little bit different. That purpose and motivation is a little bit different. People that want to fund it have different interests, different things that they're going to ask for. And so that changes the game. Modern art and modern science seem like they're really different things, but in some ways, creativity is always needed to make both fields advance. And one thing I like to point out is that art and technology are both physical things. In order to do art, you have to interact with the physical world. And because of that, you always need a technology, or you need to do something. And so you're always tied to science, because science is trying to figure out how things work and why they do what they do. And so that's something that you can never get away with. But it may be that people get complacent, that once they really know how a chisel works, they don't think that that's science anymore, or it doesn't, they're so used to using it, they don't think about it. But every artist has to know their medium, whether it's casting or even drawing. Maybe it's a very simple pencil, but at some point you have to figure out how what you're doing works. So why integrate art and science? I think I touched on it. It's important not to get too isolated and have your thinking get too, you get stuck in the ways of thinking. You want to mix things up and rattle the way you do things to allow you to still innovate. So let's talk a little bit about some of the people out there that have been integrating art and science. And these are just very few examples. There's probably so many more out there. So the first one is a sculptor, Julian Voss Andre, and he does these interesting sculptures. This one is called Quantum Man. And what he was trying to do, he was trying to capture something that I'm going to touch on later, that in quantum mechanics, the way you look at something sort of changes what information you're going to get from it. And in this case, the way he's built this sculpture, if you look from the side, from the back or from the front, you can really see this man well, but if you look from the side, he almost disappears. And he did a larger version of this, which is outside the Physics and Nanotechnology building in Minnesota. And this is a man and a woman, and you see them there, and they're quite big. You can see how large they are. And from certain angles, you can see them very well, but if you move your point of reference, in this case, you can see the woman, but the man's starting to disappear. And from a certain vantage point up in the building, these figures basically disappear. I thought this was really cool. So I really like his stuff.
What happens when snow gets there?
That's why it's stainless steel.
That ruins his whole effect. And so this is another sculptor, Anthony Gormley, and he actually worked with a physicist in the UK and talked to him about random walks and things like that. So he was inspired, and what he did is he took sort of the shape of his body, and what he did is he would take points on the, so he somehow scanned his body and put it into the computer, put points all over his body, and then he would generate a random walk from that point. And then he captured what those pieces of the walk were, turned them into steel bars, and then I don't even know how he welded all this together or made it, but it's pretty impressive. And this one was called Quantum Cloud, and then he did, so here's a few examples of that. He also made a huge 30-meter tall version that's in the UK. And from different angles, you can see his image in there better or worse. And then he did another series where he put some additional rules to saying, I don't want to have my random walk go into the image. I want it to mostly go out, so he would get a void. So he called that quantum void. And then here's another interesting guy. This guy, he was actually a sculptor and a sketch artist. And then somehow in 2003, he lost his ability. I haven't found out what happened to him, but he lost his ability to actually do the art himself. So he ended up learning how to use a camera and robotic arm and computer software to figure out how to get a robot to do his drawings for him. And so he has all this recognition software and ways of programming in order to notice features and figure out how to drive the motors to actually draw it. And it's pretty amazing, actually. Here's a bunch of examples. And he also figured out how to attach a paintbrush, which is a totally different style of movement to get painting to work. And he also has done some painting. And now I'm going to hand it off to Sam to discuss Brian Eno.
So, one of the things that Ray and I have in common is, we've been friends for 20 years, and when we get together, he lives in Boulder and I live in San Diego, we go surfing and we talk about our interests and the overlap. And, the commonality, one of the commonalities is Brian Eno. We both really like his music, and we're always trying to figure out a way to sort of apply Brian Eno's, some of the ways that he's sort of generated music and find applications for dance. And so, I've had a lot of conversations with Ray, but I think this is the first time where I actually really tried to really put these things into motion, because, it's just a completely different way of working for me. So Brian Eno started off in the 70s in the glam band Roxy Music. So it's kind of very David Bowie, but what happened was I think he might have gotten in a motorcycle accident and he was laid up in the hospital and a friend gave him some Baroque music. I think it was probably Pachelbel's Canon. So he was in the hospital bed and it kept repeating. So maybe it was a record or a tape and it was just on repeat for like 6 hours. And for most of us, that would drive us completely insane. But what he did was he realized that music could be background. So he's sort of one of the innovators of ambient music. So that's him in the studio in the 70s with the old-fashioned sort of loop tapes, reel-to-reel analog, and that's him now. One of the things that he did was he found a way to loop music, so to play music sort of against itself and sort of layer on top of it. Steve Reich is another artist who's done that. So really interesting way of working. And now we can do it digitally, so it's a little faster. He's hanging out with his friends, Bono and David Bowie. This is from one of his performances where he's put into place some certain perimeters for visual art and for music. So it's an exhibit, and so the audience is taking it in. And I'm not sure what the perimeters were for this particular performance.
But it's self-generating. That's the thing.
Oh, there we go. So yeah, I think I started listening to Brian Eno in my undergrad at UCSB. So probably talking like 1992, and I used to like play this discrete music like all the time. It actually would help me go to sleep, because it's just really, really hypnotic. But it's really interesting because here's a schematic for the way that he was able to do discrete music. So it has to do with loops and recording it on top of itself, layering. Ray knows more about this album, 1985's Thursday Afternoon.
Yeah, I can say a little bit. So Thursday Afternoon was an album. It's 60 minutes, and he basically set up sort of a sequence of instruments and it's a lot of synthesizers and things. He set up these layers, and then he just let them overlap. So he had some rules of what the type of music that would come out, and then he let it layer itself, and then he just recorded it for an hour and said, "That's it for the album." So, and it's a very beautiful album. It's really neat. And he did the same thing for Neroli, which I don't like as much, but and this is some sort of a sketch of, I don't know exactly what he was identifying here, but he had this way of taking the pieces of music that he had predetermined and layering them and adding them in a certain way. And then he didn't know what he was going to get at the output, and he would just record it for an hour. And that was his album.
So one thing that's interesting is I'm looking at this diagram, I'm seeing that it's kind of like the same thing for Pro Tools. And so one idea that I had was to take some of these Boltzmann distributions and Poisson distributions that Ray and I were working with, and I put it into a program and tried to make self-generating music myself. And it came out with something like this kind of randomized noise. And I don't think I'm going to use it for my dance piece, but it was a really interesting experiment, because it just doesn't sound so good. And also, I probably need to learn more about how to, control those perimeters. But I tried. This is some of the software that he used, Con Pro.
Yeah, the point of this one was, so he did all this, and those two albums were, he had pre-generated this stuff and then let it run. In this case, he worked with some software engineers, and they made a program where they would characterize the qualities of the music. And you would set the parameters, and then it would just generate music for you. So it was a constantly generating system that would just generate music. And he called it generative music. And I remember at the time he had said, this is what people are going to do in the future. They're not going to listen to a track. They're going to listen to a kind of music that they programmed and set up the parameters for. And they go, "Ooh, I love these parameters." And it'll just constantly generate forever. That didn't quite pass.
You kind of have that right now.
People like to enjoy a certain piece of music, but anyway.
So this is the artist Brioni Barr, and what she does is she works with algorithms and basically sets parameters, and her medium is tape. So she gets people together, and over a course of 3 days, they follow certain parameters, certain rules, and they wind up making just beautiful original works of art. It looks very much kind of like a Native American or Santa Fe kind of motifs. Sometimes it looks like circuitry.
Yeah,
schematic.
and another good thing to point out is with this type of art, you just don't know what you're going to get. You set it up, but you don't know you don't know what the result will be.
And I got really excited about this because this sort of resonated with me because I'm really interested in what dancer isn't interested in space and mapping? But I feel like that's something I've been thinking about over the years, how to map the space out. And what if I take the flat map of the space and make it three-dimensional? So this particular one sort of generated a lot of excitement for me because this is sort of how I see the space. I'll let you keep going with this.
Actually, you want to talk about these guys, so I can talk about the next one.
So Mark Baldwin and Ray Rivers. Ray Rivers is a physicist, and Mark is from the Rambert Dance Company in the UK. For some reason, a lot of these artists that we found are in the UK. So I don't know, maybe they're just more interested in this kind of idea of integrating art and science.
More arts funding.
Yeah.
That's probably true.
This is a Constant Speed. It's a piece that he was commissioned to do for the centenary of Einstein's groundbreaking ideas on relativity.
And we're going to show this
A little
video.
video.
So here we go.
Mark Baldwin has been artistic director since 2002 and is the choreographer of the company's newest work, Constant Speed.
Artistic director's job at Ron there, because Ron has always been about making new work, is to make sure that we have a future, that our present work is always heading us into the future.
Constant Speed has been commissioned by the Institute of Physics as part of Einstein Year, celebrating 100 years since the publication of some of Einstein's most important theories.
Einstein kept coming up with little phrases, and one of the phrases was that one we used in the program, which is people, animals, and cosmic dust are all subject to the same tune played in the distance by an invisible orchestra. Because things like that sort of set you off completely, that the whole world is, in a way, dancing on to the same tune. I had to learn about physics, I didn't know anything about physics, so luckily we had Ray Rivers come and talk to me as much as I wanted to about physics, and I was able to learn several basic things about this, because it was to commemorate Einstein's publication of E equals mc squared. So the three things to do with that, I was able to try and translate those into movement. And you can imagine the molecule things in the hips. And that's what just think of lifting your hips. That's nice. I just think that the whole lot is influenced by the scientific concepts that we're taking on. And the big one is how molecules behave in space and the idea of Brownian motion. When you're observing a grain of pollen in water, it moves all around the place, and it never keeps still. And this idea of perceptual motion. That was this idea that somehow you could translate into the body, especially the hips region, sort of all of energy, and it would sort of flit anywhere at all. But the sort of abstract notions of something like a photoelectric effect, the theatre thing about time, space, and light, especially dance. Those notions go very, very well with choreography. So I feel like at the end of the day, I feel I lucked out that I got the commission that I can really relate to as a choreographer.
Okay. So that's one example. Then there was another example, and this was this year. This is still touring. And I'm going to actually, we have a video for this, so I'm going to let him speak about it. But these two gentlemen were at CERN for a while, and then they interacted with these physicists to make this piece. There's some stills, but let's let them tell you the story.
Science is so lively, it's so human, it's so much about human and where we come from. It's like the story of our life as well. We are very small compared to something very big. My name is Gilles Jovin, and I'm a choreographer. We are here at BAM, Brooklyn Academy of Music in New York, and we just presented Quantum, which is a piece for 6 dancers, with the music from Carla Scaletti and the light from Julius von Bismarck. I was resident artist in CERN, and then this is the piece that I created after my residency. So it was really interesting for me to to study all these different type of physics, and tried to use some of the principles that are in particle physics to generate movement for the dance. And so the movement comes out of particle physics principles. We start with a vibration, because there's this theory that everything is vibrating, there's those strings vibrating, and it's like there's this vibration going on, and this is something that we find at the quantum level, but also in our scale. And then we start moving, and then as the piece goes on, there is like some different forces that are kind of applied to the ambient. So maybe some magnetic forces, and then they start to kind of get into one certain direction because the orientation of the fields that are coming in. So even also sometimes we applied some ideas of heat, heating up the whole system, and that makes, of course, a lot of differences. But gravity plays a big part. I didn't know that gravity was such a weak force, and basically we are really like just gently floating on top of the Earth. To know this, to start to understand this, make me kind of think that, oh, maybe we can make differently, that maybe it's an ally, it's not so much something that is, it's not a constraint for jumping, it's really something I can use in terms of motion. It's a very abstract piece. But basically, maybe one little thing that I wanted to be a bit more concrete, and is the Higgs, and because the Higgs is this particle that gives masses to the other particles. So one way to illustrate it is that we have this one dancer with a fist, and then all the other dancers are kind of rounded, and then therefore, because the fist is moving and it's slowing down their movement. There's the light on top, the choreography in the middle, and maybe the music from under. It's like really three different layers, three different worlds that just kind of get together. It's like it creates some kind of a really, I think, powerful environment.
Okay. So let's talk a little bit about the collaboration now. So you got a kind of an idea of what other people have done, and we tried to focus a little bit on some of the dance things that are out there. So a little bit on our background, since we got some background information from Adam, I'll kind of skip that part. Both Sam and I have been interested in both arts and sciences. And we know each other because we were both in Santa Barbara at the same time. And in fact, so I had a girlfriend who was very much into the dance and in the dance department, and she knew Sam, and we just sort of hit it off. And at some point, he was actually creating a dance piece, and I like dancing for fun. And he said, "Come on by, let's, come to my audition, put me on the spot." So I went and auditioned, and I ended up in his dance piece, and it was just really a great time. So that was really fun. So maybe you can say a little bit about how this collaboration started. And
so, as Adam said, I'm finishing up in my last quarter here, and I think it was my first quarter, 2.5 years ago. Ray was in town, and we went surfing, and I started asking a lot of questions about what he does, because I was really interested in specifically what he was doing, and was asking some questions around polarities and spin and algorithms. I kind of left really energized from that conversation, because it really challenged me, and it also challenged my ideas around space and the way that I could use space as a choreographer. So I kept it in the back of my mind that Ray would be a future collaborator. And we have a lot of conversations around art, science, math. So we find the elegance in this, and it's something in common that we have. So the first thing that I'll get into how it happened, but the first, I think, agreement that we had was we didn't want to be too literal in this collaboration. So I didn't really want to show how the particles spin or anything like that. I didn't really want to do a superficial collaboration where he's just a consultant. I really wanted to be involved in knowing and learning some concepts, and him coming in and working with the dancers, which actually happened last night. So we talked about some ways that we could generate some choreography. We set some parameters, and that was really exciting. I didn't know how that was going to work because typically I'm a choreographer who comes from a place of making work from a very autobiographical place, or from literature, or from sort of pathos or theater. I tend to like to put a lot of layers into my work. I like this sort of state of liminality, and Ray is sort of very focused in what he's interested in, and also just very precise and how to talk about what he's doing. So that's something that we kind of enjoy, is that tension. And this is your part.
Yeah. So now so I'm going to just introduce some of the physics ideas, and then we'll talk a little later about how we incorporated them in. So the first thing I wanted to mention was the law, Newton's laws, and classical physics basically leads to a deterministic universe. And at the time, this was interesting because people sort of felt if you had all the information about all the particles in the universe and what the initial conditions were, you essentially knew everything. And so everything was considered deterministic, which was a problem for free will. And so definitely there was many philosophers and arts and many people that did not like this, but it was sort of reassuring to some people that everything was already laid out. Quantum mechanics sort of changed all that. Quantum physics is inherently random, and it leads to an indeterministic universe. And I like this quote from Anton Zeilinger, and he says that not even God knows what's going to happen. So if you have an individual event happen, there is no cause, and no one can know what's going to happen. And of course, Einstein didn't like this at all, and he said, God doesn't play dice. That can't be right. So I'm going to review some principles that we're going to use, some concepts from quantum physics, and quantum superposition is one of them. And that is that the wave function for an object can be made of, a simple one is made of a collection of different energy states. Different eigenstates all are involved in creating a wave function. And the concept of quantum entanglement, and this is where you have multiple objects that are in this interesting state where they have these non-local correlations or interrelationship. And a strong measurement, if you extract information out of one of the objects, then you sort of instantly determine the state of all the objects, regardless of their physical separation. And the thing to really understand here is that this interesting state it's unknowable before information gets drawn from it. It's not just that it's well defined and nobody has the information. It's that it's in a state of unknowability, and as you extract information out of it, then it has to choose. Then it chooses something, and this is the fact that if you have multiple objects and you extract information out of one of them, the other ones, their possibilities change when that happens. And Einstein hated this also, and he called this spooky action at a distance. And so these are the main concepts we want to try to put into our piece. And the other one is this idea of measurement. So what happens when you measure a system? So it's not possible to determine the wave function of an object from one measurement, because when you make one measurement, you get one physical observable, you get one particular instance, but there are many other possibilities that can happen. You're only picking one of those out. And the strong active measurement, which gains maximum information, and essentially during that process, you're collapsing the wave function, or you're making the system pick a definite state, an eigenstate which has a definite value. And that choice is completely random. This is where the complete randomness comes from. There's no cause and effect that we understand that determines which thing you actually get when you make a measurement. The other principle is complementarity, and we didn't necessarily put this into the piece much. This is a tricky concept, and this is the idea that if you have two observables, they're somehow different from each other, but they have a relationship. So if you know position extremely well, then you don't know as much about momentum, and vice versa. And to just give you the flavor of these things, to remind you of these things, I came up with a funny cartoon example. So if you imagine Alice is measuring the Cheshire cat, she can see this cat standing up, or she can see him upside down. So those are the two states, the only possibilities that she has, say. However, from a complementary point of view, if she sort of turns her head and tries to look at the cat, she sees him lying left or lying right. So if you imagine the cat is starting in a superposition state and Alice makes a measurement of the cat, she's either going to get down for that measurement or she might get up. Okay, and the amount, if she does this many, many times, these coefficients A and B tell her essentially what she's going to get. A squared tells her roughly what's the probability of getting up, and B squared tells her the probability of getting the cat down. Now, the interesting thing is if she does a measurement and she gets a particular result, so she knows everything about up, from the complementary point of view, she has no information now. So these are 50-50, so they have the same coefficient. She knows everything about looking at it this way, but she knows nothing about looking at it this way. So if she then goes and looks at from that direction, she's going to have a 50-50 shot of finding left or right. Now, if we have an entangled state where you imagine now the cat is entangled with the queen, and you're in this situation where if the cat is up, then the queen is happy. If the cat is down, the queen is upset. And she takes a measurement of the Cheshire cat. If she finds up, then it means the queen must be happy. No matter where the queen is, we know the queen is happy. And likewise, if she sees the cat down, then the queen must be upset. So you can expand this more. So if you imagine now you have three, you have the Cheshire cat, the queen, and the white rabbit, and you create a state like this, this is a very interesting state because if you measure that the cat is up, if Alice takes a look and sees the cat up, then she just knows the queen's upset and the white rabbit isn't doing anything. So not so exciting. However, if she measures that the cat is down, what's interesting is that there's still entanglement survives between the queen and the rabbit. This is an unknown system now. It's still in an unknown state, even though there was a measurement performed. So this entanglement survives, even though she only gained information about the cat. So that's an interesting thing. So the next thing I'm going to talk about is the quantum harmonic oscillator, which is the system that I work on. I'm going to say a little bit more about that. And just to remind you, this is the potential energy of a harmonic oscillator. It's quadratic with position. Classically, it has a continuum of energy states. Quantum mechanically, we know it has to break itself up into energy levels. And here I show the wave functions for those levels. And there are definite energy eigenstates with eigenvalues. And here I show the eigenvalues. And the spacing are equal spacings for a harmonic oscillator. And so here's an example of a harmonic oscillator. Classically, it sort of moves around in phase space. And if you apply a force, a harmonic force, this actually isn't working, but that's supposed to be going back and forth. But if you apply a harmonic tone to that oscillator, you generate a state that sort of goes around and around in phase space. Quantum mechanically, of course, it actually has some uncertainty, and this is the Wigner function, which shows sort of a cone blob. So it's still rotating, but it has some uncertainty associated with it. And this is a superposition of energy eigenstates. That's what creates this kind. It's a coherent superposition of these eigenstates that creates a state like this. This is the state that actually oscillates kind of like a classical oscillator. Whereas if you put the system in an eigenstate, it doesn't really oscillate. Now, this coherent state is a superposition of these energy eigenstates, and the distribution of the prefactors for all those wave functions for those eigenstates, that tells you something about what's going on, and that forms a Poisson distribution for those coherent states. So this is a case where the average energy or the average occupancy is about 5. And if I crank that up, it just sort of moves out. And you get this probability of finding the eigenstates nearby the average energy. So that's what that distribution looks like. And that's your Poisson distribution. But you can also drive this oscillator sort of with random noise. So that's working. So that's your sort of picture where you're just sort of jiggling this thing. And this is your quantum uncertainty in the oscillator. But as you add thermal noise, it just looks more uncertain. It's still very noisy. So this is an incoherent mixture of states. So this is an incoherent mixture, and the distribution for these states looks very, very different. So here's your average quanta of 10. You're most likely to find the system in its ground state, but then as you move up in energy, you can find it there, but it trails off. And as you add more energy, it moves over to the right. But it's a very different distribution, and it's incoherent. That's the Boltzmann distribution. So we have the Boltzmann distribution and we have the Poisson distribution, and these were the things that we wanted to try to, for an oscillator, put them into some sort of a physical dance. And we're interested in trying to show the quantum aspects of this motion, even though typically people would think, oh, this is Brownian motion, that's kind of classical, and this is harmonic oscillator motion, it's kind of classical. But there are quantum aspects to that motion. And so this is related to work that I actually work on. I'm going to come back for the performances from January 20th to the 26th. I'm trying to get a talk in the physics department. We'll see if it comes out. But I'm going to talk about some of measuring quantum fluctuations in a real mechanical oscillator. And what we make at NIST are these microfabricated circuits. This is an aluminum circuit on a sapphire membrane. If I can use my laser pointer. And this drum is actually an oscillating drum. And there's a gap here. This is too bad this turned out. So this is a 50 nanometer gap. There's a bottom electrode and a top electrode with a 50 nanometer gap. And this top drum is moving around. This piece that you see here, and this is oscillating at 10 megahertz. You can't see that too well, but forms a capacitor. This is a coil inductor. So this is an LC resonator, electrical resonator, and that resonates at 10 gigahertz. So when this guy moves up and down, it changes the resonant frequency of the higher frequency system, and it gives us some information about what the motion is doing. We fabricate that on a chip, and we have a mechanical oscillator on one side. We also have superconducting quantum bits, which is sort of like an artificial atom. We mount that on a dilution refrigerator and cool it down. We attach all our equipment, and we do all these measurements. We've got the mechanical oscillator on one side, and we actually use a quantum bit on the other side, which is this artificial atom, in order to help read it out. And of course, I don't have time to talk about it all now, but it's sort of related to quantum electrodynamics. Cavity quantum electrodynamics was developed by Dave Wineland and Serge Haroche, and they got the Nobel Prize in 2012. They were able to use the artificial atom to interrogate the oscillator in order to measure these distributions. So these are a thermal state distribution, a coherent state distribution for both atomic motion of a trapped ion and electromagnetic cavities that they sent atoms through. So we have done the same thing, but for this little micromechanical oscillator. So here's some actual real distributions we measured. And we can see anything from, this is supposed to be 10 to the minus 2 photons or phonons to about 10 to the 10 of those. So that's it for the quantum physics piece.
So, like I said, I started dancing at UCSB. I was about 19 years old, which is pretty late to start in dance. I was an athlete, so I felt like it was pretty seamless. It was a pretty seamless transition. I was a runner and a wrestler. But one of my teachers, I was fortunate enough to study with Alice Cornadina, who was a principal dancer in the Jose Limon Company. And Jose's technique really resonated for me because being a Mexican-American and also Native American, and also being, my family was from Sonora, Mexico, and that's where Jose was from. So there was a lot of sort of resonant, I really resonated with his technique and his vision. One thing that I learned in class was this idea of isolating. So my teacher Alice said, you know, the head doesn't always have to lead the body. There can be other parts of the body. So what if your shoulder leads? So then I can move my shoulder through space. And how does that transfer information to the rest of my body? Or what if my elbow moves through the space? So just this idea of different parts of my body leading through space gives me a real ability to kind of negotiate space, but also find inventive ways of moving. So that really informed my work for many years as a choreographer. Martha Graham was sort of the grandmother of modern dance. She's a person who decided she found a way to take away this whole idea of trying to fight against gravity, because ballet is always sort of trying to go against gravity, trying to look like they're floating. And she said, well, you know, I'm going to the floor. So she found a way of doing contractions. There's this idea of contraction where you start from the core and you breathe out. So this was all really a kind of inventive way of moving that no one had ever seen this before. So she was truly a groundbreaker. The thing is that it developed a kind of model for choreography in modern dance. So as a choreographer, you walk in and you're the god. So the dancers do what you tell them to do. And this requires a certain, the dancers are really, really adept. They're able to like learn information and record information at the same time and be in their body. Yvonne Rainer came along in 1964 and said no. It was just sort of this proclamation against this idea of the choreographer as the god and the sort of virtuosic and the heroic, all these ideas that really informed Jose Lemon's work and Martha Graham. But this came along the time where John Cage was doing some really interesting things, and I think it was just, historically, the 60s were really activated. But the interesting thing about Yvonne Rainer is that she really kind of broke that idea of how modern dance could be. So it's always, there's the Martha Graham technique, there's the Jose Lemon technique, there's the Paul Taylor technique. So people had sort of their schools. And what she was saying was, this is dance. I'm dancing, so I'm walking. Adam's dancing. He's sitting here. So it's this idea of pedestrian movement as dance. So there's an example of Merce Cunningham's work, Rainforest. One of the things that I loved about Merce Cunningham was that he was able to take different elements and put them together at the last minute, right before the performance. The dancers didn't even know what they were going to do. So he had certain perimeters. He had collaborators. John Cage would sort of construct a sound score, and then they would just mix it up. So the dancers never knew what was going to happen, and each performance was different. Interestingly enough, Rampart from the UK brought it back in 2010, which is, it's really kind of an amazing way of archiving work, keeping it alive. For me, Pina Bausch is a huge influence. She died, I think, in 2012, but she found a way of sort of juxtaposing different ideas, sort of theatrical and dance, and was able to sort of put these two things together. But a lot of times her work is very emotional, comes from a very sort of deep place of sort of pathos, and this is her interpretation of Rite of Spring. And the reason why I mention all these dancers is that they throw a really big shadow, a very huge shadow over the rest of us who are trying to make work now. So how do you find a way to negotiate this? We have all these innovators who just broke all the rules. Well, what if all the rules are broken now? So how do we go forward? So, I think it's really important to know what's been done, to research, to find the information and just constantly stay in conversation, but then also challenge oneself to innovate.
So we're running out of time, so maybe we'll skip that.
This is just a photo from one of my pieces. Deer Spine, this was, I made this piece last year. It's based on my Native American heritage. I used the Native American medicine wheel as a map. So the score was basically whatever direction that my body landed, I would do that score. So I had a phrase for fire, a phrase for earth, a phrase for summer. So wherever I wound up facing, that sort of informed what happened in the dance. And so each dance was different. Each performance was different. During the choreography of making this work, I came across this idea of using the Fibonacci sequence as a way of sort of subverting any way of approximating Native American dance, because I didn't want to do that. I didn't feel like it served, my heritage. So that's when Ray got involved. I called him up, and when we showed this,
We could show it, or you could do it. We could skip.
Yeah, so,
Up to
so
you.
yeah, no, we're right here. So the Fibonacci sequence, this is from the Yaqui tribe that I got this idea from, but they had a certain way of stepping, and I could never figure out what the count was. I was watching them do this ceremony, so I came up with this idea of the Fibonacci sequence. So it goes 1, 1, 2, 1, 2, 3, 1, 2, 1, 2, 3, which is 5. 1, 2, 3, 4, 5. 1, 2, 3, which is 8. 1, 2, and then I just go to 13 and I go back down. So this was a way that I was able to sort of incorporate some ideas around my heritage, but then still, keep it so that I wasn't just, sort of like just taking from this heritage and just putting it on. You want to show this?
I'll show this because it's so fun. We got to show it.
I came across this in my research.
忍者の皆さんと一緒一歩進んで前ならえ一歩進んで前ならよ振り返るで手のいい子一度振り返るでちょうどちょっとそこだけ違うよちょっとしゃがんで違うよちょっとしゃがますし広い空気が晴れますし一歩進んで前ならえ一歩進んで偉い人振り返るで手のいい子一度振り返るでちょうどちょっとそこだけ違うよちょっとしゃがんできな広いちょっとしゃがますし広い空気が晴れますしそうとそうと終わりかなそうとそうと終わりかなそうとそうと終わりかな終わり
So, well, actually, quickly, you could say that was
Yes.
it was a Japanese educational video for kids to
Yeah.
teach them about algorithms.
I was trying to educate myself on algorithms, and me not coming from a science background, I spent some time looking what is an algorithm, how does it work, so that you have different ways of using algorithms in computer programming and science, and then I was wondering if anyone ever utilized it in dance, and that's all I got. So that was sort of fodder for me because I thought, well, I could probably do something a little more advanced. So
we're running short on
Yeah.
time, but you can quickly zip through. This is the outline of what we were going to talk about, and we'll try to go through it as quickly as we can.
Okay, so starting off with this collaboration, Ray and I talked about how we could work, and he suggested that maybe I come up with 10 phrases that build up an energy. So I went into the dance studio, and I kept feeling like I was trying to show.
Oh,
I
wait.
was trying to show choreographically the particle and the cloud, and so what I did to subvert that was I used some of Brian Eno's techniques, which are called oblique strategies. So they're a way of sort of giving creative impulse in the process.
Let me quickly say, the basic idea was to take the energy levels of the harmonic oscillator and attach a phrase, a dance phrase, for each of the energies. That would represent the energy level or the wave function that was actually happening. And then now go ahead. But we had to create the phrases. So
Yeah. So in creating the phrases, I had to find a way to sort of trick myself because I kept thinking about the audience and what was I showing the audience? I needed to show them the particle and the ball of energy. And so this was a way that I had to sort of trick myself. Don't be frightened of cliches. So there's a little bit of ballet in there. There was a couple other cards that I pulled. Tesla balls was another one. So bouncing off this idea from Jose Limon, this idea of the body parts leading through space, I came up with this idea by basically taking a map, a two-dimensional map on the floor, and then turning it up into space and then sort of making it into three-dimensional. So if I had a Tesla ball here, and another here, and another here, and another here, and one more here. So I have to assign a point of contact with each Tesla ball. So if it's here, I could use the top of my head. If it's here, I could use my shoulder. If it's here, I could use my elbow. If it's here, I could use my foot. So I do this, and within 10 minutes, I have choreography.
and maybe we should show it. This is short, so
Yeah.
we could show this one.
So this is Anne's Tesla ball phrase.
Okay, so I basically generated a random sequence of numbers up to from 1 to 9, imagining that it's this harmonic oscillator with a Boltzmann distribution and a Poisson distribution. And then Sam created the phrases for each of these numbers. Now, maybe since we're running short on time, you could
Why
do
don't you
the,
keep talking and I'll show
Okay,
them
yeah.
the movement.
do the phrases.
Yeah,
That's
yeah.
good.
So keep going.
So yeah, okay,
This
so
is one.
that's great. We're multitasking here.
This is
So
two.
what I did is I generate the Boltzmann distribution for all these different phrases, and I did it 4 times for 4 different dancers. And what you can think about this is all 4 dances is one harmonic oscillator, and these are different, essentially different pieces of that superposition.
4.
And each one has a, it's great. They have to watch you and what I'm showing at the same time.
It's working.
Each one of the distributions looks funny because we don't have that many numbers, but that is a Boltzmann distribution because we don't have that many phrases. Anyway, I did this for the Poisson distribution also. We also did something called the non-canon, and this was everyone does these 9 phrases, and this was inspired by Eno, but each person has a different time. The rate at which they're doing them is different. Some people start off slower and speed up. Some people start off faster and slow down. Some people do it at a constant rate. Some people speed up and slow down. I had to discretize that, so it looks kind of funny.
9.
And then the other piece was, if you tell a dancer, do phrase 3, they have no idea what you're talking about. So after doing the phrases, I guess you can explain like the way the phrase is hug the world came from the fact that you're doing the hug
So
and crumble.
originally when I was choreographing it, we called it phrase 1, phrase 2, phrase 3. And the dancers like they just really didn't vibe with that. So in the making of them and showing them, I would say, okay, so it's like you're crumbling something. And I would just be saying this as I was making the choreography and showing them. And this one's hug the world. So then we had to change the name of phrase 1 to crumble, and phrase 2 to hug the world, and phrase 3 don't hug the world, and phrase 4 much ado about nothing, which I don't even know how this is much ado about nothing. But you have sort of these funny little titles for phrases.
So that what I showed you there was a little bit of code that had the name of the phrases, and I generate the distributions, and I turn the distributions from numbers into phrase names, and then we had to find a way to tell the dancers what to do. And let's see if I can figure out. Here we go.
Who should I be? Sandra?
Okay, there we go. So basically what we had to do was display to them these things. And this is actually, we set this on auto run. And so what they see is a countdown. And what they see, the first thing they see is what phrase they're on. So Aaron's on much ado, and it's counting down. The counts are counting down. So the counts tell them how fast they're supposed to go. And the little arrow tells them what's coming next so they can transition to the next one. And this was very tricky for them. This is not the way dancers learn how to do their dancing. So that gives you a feel for it. So that was something we didn't even know we were going to have to develop.
Yeah, so one thing that happened is in the rehearsal process, I handed each dancer a phrase of like maybe 54 sequences. And so it's a Sandra,
How do I get
5,
this going
1,
again?
3, 2, 8. And she would look at it and be like, and how are they going to memorize 54 sequences of just numbers? And so what I saw Sandra do was she took this sort of script and wrote the names of the phrases next to it. And then that gave me the idea that maybe I could just put it into a PowerPoint and do a teleprompter.
Okay, so this will give you a feel for some of the movement. This is the Boltzmann. This is what it ends up looking like. So one thing you notice is sometimes they are in unison and sometimes they're not. And and it creates this really interesting effect. And again, you can imagine these are all one oscillator in this superposition. They're doing all these things at the same time and quantum jumping around from phrase to phrase or state to state.
And there are 4 dancers in this piece, but
Yeah, this was
one dancer was sick.
okay. And let's go to the next. So this was neat. So this is the non-canon. Some music. So an interesting thing to mention is, so it's a great collaboration because I'm not telling Sam a lot about how to use the space, but I'm trying to set up some rules. So that was an interesting, he decided let's put them in a big cluster in the beginning and see how it goes.
Yeah, there weren't always these sort of ideas of I'm going to take this literal concept, but I really believe strongly in this idea of embodied scholarship. So if I'm really sort of educating myself and learning it in conversation, there are ways that some of this information is able to distill through my body and through the choreography. So that's the hope. And so some of these ideas have nothing to do with Boltzmann or Poisson, but I still find ways of sort of, setting parameters and giving prompts and creating choreography that is still not coming from a narrative, a preset narrative.
Maybe we should probably wrap up.
Okay, so we'll skip this. If anyone wants to stay, you can see some more examples of how do you generate entanglement, how do you show entanglement with the dancers, and then there was lots of things we had to figure out for how are we going to do a quantum measurement, and then other factors like staging, lighting, costumes, and then the fact that Sam and I were not non-local. This is the first time I've been out here for all this development, and we really relied heavily on Vimeo and Google Chat, Google Hangout. So what have we gained? This is pretty much the end. I mean, and I'll put this ad up so you can write that down if you want to come see the show.
What I've gained is just a very a way of being much more clear in my choreography and my process, a way of talking about my work that is clear. Like I said, I reside a lot in this liminal state where I don't really want to talk about the work because I feel like it sort of limits it. But I found, and the more that I can describe some of these ideas, the more sort of it generates more ideas. So I found like this is a really rich and fertile area for me to keep investigating, and I hope that Ray and I will continue to develop this piece.
Yeah, and I've had it's been extremely fun for me to work on this. And I'm an experimentalist, so I like the idea of trying something and seeing what happens and what comes out of it. And so it's really neat. And plus the unknown, that when you embark on some project, you don't know what's going to come up, and it's just fun to see how you deal with those problems and try to find a solution. And you learn things you just would never have known until you embark on it. And and there was always this question of, well, will this artistic endeavor influence the science? And we'll see where that goes. I mean, I definitely think that it changes the way I think about things, and that'll always add a new idea.
So yeah, here's the information for the show. It's in 2 weeks, and love it if you could come and see it. I mean, this is part of my mission, is to engage the community here at UCSD and bring you over to our side. So come over to the dark side. So yeah, thank you so much.
So I know it's after 5, so folks have to leave. Go ahead, but if there's any questions, please ask away.
Yeah, any questions? And we can go back to show some other examples if you want to see them.
So a lot of the sort of presentation of this art to the public happens in the form of sculpture or art album or performance. And in the science analog, that's a paper, a publication. So you showed a lot of examples of productions and so forth that were inspired by science. Do you have any examples of, say, publications that had the inverse, influence, where some idea came from art and it led to, wow, now look at this publication?
Well, we got an example. We gave this talk yesterday in the humanities, and someone pointed out that Feynman diagrams may have really been inspired by his ability to paint and the artistic endeavors he was in. So if you include quantum electrodynamics, hey, that's a pretty good contribution there. That was an important one.
But the question that you raise is it really sparks some interest for me and some additional research and finding out, because I don't think it can just be a one-sided exchange. There needs to be a dialogue. So a lot of times it is art that's inspired by science, and I would love to see some innovation that's happening. I would challenge artists or scientists to live in that liminal place, to not know, and to keep finding things, but to be in that space of liminality and to not always have to be in this place of knowing all the time, like pushing against it, pushing against the edge. I think that's how we innovate in the art world. And I know that these are really different disciplines, but yeah.
The referees would probably have something to say about that.
Yeah. Yes.
This is more of a comment on the historical background, classical physics versus quantum physics. We usually think of, as you pointed out, Laplace and then later Heisenberg and so forth. But actually, the same patent was held back in real classical times. The Greek philosopher Epicurus taught that as things travel, they occasionally swerve unpredictably. And people have seen that as an anticipation of quantum physics. And I looked at Heisenberg's writings. He's written on the history of science, going back to the atomic times. And although he talks about Democritus and all those other people, he doesn't talk about Epicurus. So I thought this is a fascinating area which possibly could be explored. This swerve could be put into dance too.
Mm-hmm. Well, in fact, what's funny is we were trying to come up for a name for this piece, and there is a term, I can't remember, it's clementis or something like that.
Chlamydium.
Was it chlamydium? I don't know what it was, but there's a term for this, this idea of an atom wanting to swerve. And we thought about putting this into the title, and instead we went with dunamis, which was, he's going to look it up, but
it's something like that, begins with a C.
Yeah, and so we actually looked into that, and yeah, the Greeks all had a lot of really interesting ideas and different factions that would, crop up of who they believed in and what concepts they believed in, and they actually believed that chance had to be a natural part of nature.
Well, the Epicureans.
Yes,
the Stoics.
That's right. That's right. That's what I mean. They have these different camps. I guess the difference in the modern world now is we actually, with real modern science, we actually go and do the measurements and test these things. And that's another interesting thing about with, Einstein and Bohr. They had all these thought experiments, but, Dave Wineland and Serge Haroche, who I showed, they got the Nobel Prize because what are they doing? They're actually doing those thought experiments and finding out the actual answers and testing those thought experiments. It's pretty amazing.
Yeah, so there was this aleatory stuff, music, where they have chants in it, like Cage or like Worst Cunningham, and sometimes when I see people use chants in artistic compositions now, they there's still a lot of decisions that are being made. So you had the chance, but you staged it, but making the people go in a certain way. You chose the original syntax, the original forms that you were going to use in the sequence. Now the sequence was generated by the use of the distribution, chance over the distribution. So I'm very interested in this problem as a chance, as a stimulus for creativity. But what I find is that the chance isn't taken, I mean, Cage did it literally, but you got that stuff, and people don't do that stuff much any longer, at least not, it's not so interesting, but the chance as a stimulus to see something which then you iterate on and refine, that's quite common now, isn't it?
Yeah, I mean, one of the things that I've kind of pushed against in this program is that it's the values in the dance program are very postmodern and really coming from that place of you know, John Cage and chance and randomness. But the thing that I push against is that I feel like the perimeters are too wide. And so what happens is if we have an improvisational class, that the 3 or 4 of us who are in the program just wind up sort of dancing in the space and moving around. And I feel like there's a real hunger for some kind of parameter, some kind of framing. And so I think just in being in that process, I've kind of had to refine what I think as improvisation for me as a way of informing my work, because I can dance all day, but if it's I want it to have some kind of, I want to be able to speak about it too.
I mean, I guess one of the things is true randomness is quite boring, right? No one wants to watch snow on a screen. It's very boring. But how do you sculpt randomness? Like we were talking today about filtering. If you filter randomness, you actually get things. And what and with the generative processes we're talking about with Brian Eno, what we're trying to do is set up rules and this this rule-based thing, but you inject the randomness in as a source, and you get something interesting out. And we didn't mention, but Brian Eno was really amazed by that little screensaver from the 80s called Life. I don't know if anyone remembers this. They had little dots on the screen, and they had very simple rules of if there are too many dots near each other, some dots should disappear. Randomly, dots can show up. And if there's a certain number of dots, more dots will grow. But if there's too many dots, they die. And you start off with a few dots on the screen, and then you just run the thing.
Yeah.
And there's random chance in there, but you get all these neat patterns, all kinds of complex stuff forms. And that was kind of one of the things that spurred him on, that it wasn't like you just get garbage, but actually beautiful patterns arise based on rules and randomness. So that's kind of where the rules are trying to sculpt something, but you don't always know what you're going to get. So, and I think even as an artist, you have, and you have to decide whether you like what you generated. Was it?
And there is the reality of
that's a wide realm.
Working with designers, that I have to be somewhat specific in how long the piece is and what's happening in this section. And so there are just the constraints of working in this theatrical environment. They call it the LORT model. So it's the traditional theater model. So we have people who are working in the shops, and we have lighting guys, and there has to be a certain clarity of just communication in that way. One thing we were talking about last night was, the next piece, the next time we make it, is it possible for Ray to actually generate some of these sequences in real time by running this program?
Even though they were pre-generated, it's just a technological issue to have it actually being generated at live, broadcasting to the screen, and then the dancers do their thing. So we could have a source that's actually a photon random number generator that is real quantum randomness, but it gets communicated to the dancers, and then what they're doing is
you gotta
truly.
base it off of sensory things on the audience. So there's feedback, and then it might
That's a possibility too. You could try to look at their faces. Are they liking this? Let's change it and see if they start to smile more. Who knows?
As you know, Dirac emphasized getting beauty into one's equations. He emphasized that very much. So how do you measure, or can you measure, which of these sequences is more beautiful than the other?
Hey, we have an answer for that. So one thing we noticed when we did this, we would do a rehearsal and let's see what happens. And when we saw people going into unison together, we thought, wow, that looks really neat. You see all this chaos, and then people start to come into unison. And then when they break free of that, it's kind of a shock. You sort of are pleased by the fact that you understand what's happening, and then it goes random again. We call that sparkle. And because I'm generating the distributions, I said, hey, Sam, I can go and measure the sparkle. I have the distributions. I can go and ask, how often do I see 2 dancers together, 3 dancers, or 4 dancers all on the same phrase? And so we actually sort of measured the sparkle during the sequence, and we decided to choose certain pieces that we thought had more sparkle.
Doesn't traditional dance do all sparkle all the time?
Yeah. Well, if everyone wants to see that kind of gives, that was one of the motivations we had for showing entanglement. So the idea that things are correlated when they're in an entangled state, it made it really easy for us to say, well, how should we show entanglement? The easiest way is not to show 2 things in a weird opposite, spin up, spin down, and up, down or something, but to show that they're all together. So this was an example of all the dancers having a part where they're doing the phrases in unison now.
For the most part.
For the most part.
They still need to rehearse.
So the idea is most of the piece, you're not seeing this. So when it happens, it will be special. It's unique. It's different. And we're going to, that happens after their process of getting entangled, which was, in real physics, you have some sort of a force between two systems. In the superconducting circuit case, you have an actual coupling capacitor or an inductor. Thank you. And that forces an interaction between the 2 systems. And if you put them in a quantum state and turn on the interaction, you can get them entangled. And so Sam sort of came up with this. Maybe you can explain how you came up with this.
Yeah. So this is, I made a game out of it, and I called it the touch phrase. So basically what I said was you could have two turns. So Anne could say 1, 2. So she had to go and touch another dancer. Didn't necessarily have to be with her hands. It could be 1, 2. But she has to make contact with another dancer. So then she says 1, 2, and then Erin might say 3, 4. So she's touching another dancer, and then the next dancer does it. So then we build it up. We go all the way to, I think we went to 12. And then I had them sort of build this machine, sort of connectedness, and then step out of it and remember their phrase in the sequence. So if I was to do ands, it'd be like 1, 2, 3, 4, and 5, 6, 7, 8, blah, 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 blah. It goes through the sequence, 9, 10. So that's how we built this little phrase.
Yeah, so they get into this situation where they interact with each other, and then when they leave, they go into the condition where they're all simultaneous and they're in unison. And we have a script for that runs. The PDF is running, so they always know where the unison is and what phrase they should be on. So as soon as they're done with the entanglement, they can figure out how to get back into phase with each other. So here's that touch phrase. Oh, and before they're entangled, they're kind of doing their own thing. That's what that is.
Thank you.
So I think that's it. Thanks, everyone.
Thanks, everyone.
Appreciate you coming.